When I did my PhD, it was year 2005, I was asked to help in a large German consortium project. We were 17 partners with best universities, with large robotic companies. KUKA, Schunk, DLR, Siemens, everyone was on board. We were building assistive robots for elderly at home. This robot could detect and recognize objects, could grasp them. It could move around, could follow humans. It could follow a pointing gesture. That was my bit. I would claim that that robot could do autonomously more than Elon Musk has shown us so far. And to put things in perspective, year 2005 is a long time ago. This is the year when the first YouTube video was released, and it's still 2 years before the first iPhone. Fast forward 20 years. We have robots that dance. We have robots that fight. And we have robots that you can remotely control to collect data in people's homes. This is impressive. However, if I look around, I still see people doing a lot of the 3D jobs. That stands for dirty, dull, or dangerous, or all three of those. Think of jobs in construction, in mining, in agriculture, in healthcare. These are jobs that are bad for your back, that are bad for your sleeping cycle and family life, that might be bad for your mental health. Wouldn't it be nice to have assistants in all those jobs, robotic assistants? I'm a mother, and I raised my children along my academic career, and I can tell you I was doing a lot of dirty and dull jobs on a daily basis. Now imagine how much talent we could release if we would have some assistants in those jobs, or maybe even automate some of them away. And it might be a chicken and egg problem, because I believe if we would have more women doing robotics, we would have much more useful robots sooner. But joking aside, where are all those robots? Are we almost there? Do we just need to double down on collecting the data, training large models? Or are we on the wrong path? Let's think about that. To stimulate your thinking, I have a little task for you. Can you take your hand and put it in front of your eyes and then move it back and forth? You see, it's like smeared. Guys. Now keep your hand still and instead move your hand back and forth. It's less smeared. Why? What happens? What happens in your head? How many times during the day do you think, like, what happens in my brain when I do this or that? Why is that important? What does it have to do with robotics? Now I have a riddle for you. What do all robots and all brains on this planet have in common? Absolutely all robots and absolutely all brains. I'll tell you. They both exist in order to generate movement that goes against physical forces, like against gravity. Like something is pulling me. No, I don't want to go there. I want to go here. Intentional movement. Why is it interesting how brains do that? Well, because the biological systems with the brains is our only working example for generating movement that can support people in all those dirty, dull, and dangerous work. So I believe it's absolutely necessary to understand how do brains do that. Let's dive deeper into this question. How do robots generate movement today? They do this with motors. Motor is a device that can control position of a joint. And motors do this blindly, which makes robots dangerous. In order to make robots that are safe, we need to enable them to see obstacles and what is around them. How do we make robots see? Well, for the last 200 years, we have a device for that. It's called a camera. Cameras make images, pictures. Pictures are nice. You can look at them. You can extract a lot of meaning from a picture. Now, if you try to use a picture to control a robot, you will discover it's difficult. In fact, computationally, this is one of the most challenging tasks, not only for robotics, but also for computer science in general. It is for this task that people even invented their own hardware called graphic processing unit, or GPU, to show images on a screen. And today's field of AI, the artificial neural networks, were also developed to process images, to recognize handwritten digits, to detect traffic signs, and then all the other objects. And until today, it is the most challenging task. In order to solve it, you have to first collect a lot of data and label it. Then you have to train large neural network for weeks, sometimes months. And then when it's running, you need a big computer to run it. Sometimes you need to build a little power station next to your computer center in order to do image processing tasks. Now, biological systems don't seem to have so much of a problem processing visual information. Even a little fruit fly, as it flies around, can avoid obstacles, can go to targets, and can deal with the visual information easily with something like 100,000 neurons. This is less than in one layer of today's artificial neural networks. How do they do that? How do biological brains process visual information? There are a couple striking facts about how that works in the brain. So I'll tell you a little bit about that. So in the brain, the visual information from our eye first goes to the back of our brain. This is where first level of processing happens. Some simple features are extracted, corners, edges, and then from there, the activation goes like to frontal areas on top, and with more complex processing. And here you do face recognition, the face of your grandmother or the car or the cup. So this is from input to output, this bottom-up processing. So the striking fact about the brain, that in the brain, these connections that go in this direction, they constitute 5% of all connections. 95% go in the opposite direction, from top to down, to bottom and left and right. Just to contrast it with artificial neural networks. In artificial neural networks, and I have selected the one we all know and love, the transformer architecture, from the respective paper, but in all of them, the connections that go from input to output are approximately 100%. And it's approximately 0% that goes backwards. So there's 95% of connections in the brain, in the visual pathway, that are not accounted for in our AI. So if someone tells you AI works like the human brain does, and it's like almost human, you can laugh into their face, because it's very hard to be further away from the truth. But for us, the question remains, what do these 95% of connections do in the brain? And what they do is the following. In the brain, those connections form loops. They form circular structures in which activation in the brain can reverberate, can walk around, forming dynamics, forming neural dynamics, a dynamical system. Dynamical system is something physicists love, because for physicists, any physical object has some dynamics inside it that gives rise to its properties. Computer scientists don't like dynamics very much, because all these loops, they make it really difficult to prove their theorems and work with that. However, for us, it's very important to understand neural dynamics, because it lies behind very important cognitive functions. For instance, decision making. If I, based on some little evidence, make a decision to, for instance, support a certain political party or view, this will change how I perceive the world, because now I will have a slight tendency to ignore all the evidence that goes against my decision and actively seek for evidence that supports my decision. Welcome opinion bubbles and polarization. Another example is learning. If I want to learn something, it's not that I can observe 10,000 videos of someone riding a bicycle and then I have a representation of how to do it and I can do that. No, I have to engage with this process actively. I have to try things out. I have to fail and learn from that. It's all about dynamics. And these dynamics, it's not only going on in our brains, they also go on through the sensors with the outside world, with the environment around us, with other people, in the beautiful, dynamical dance of true intelligence. Now, this is not the only property which I want to mention today. There's another one, and it's diversity. And this time, I don't mean gender diversity. I also don't mean neural diversity. I mean the diversity of algorithms that our brains implement. Our brains are not just big bag of neurons with connections that are adjusted by evolution and learning. There's a lot of structure in the brain. There are different regions in the brain, and in each region we have different neurons, different motives between these neurons, different network structures that support different dynamics and different learning rules. For instance, cortex is a prediction machine. It always looks ahead. To the contrast, the basal ganglia, the structure inside our brain, is busy thinking what to do next and when to learn and what to learn. While hippocampus holds spatial representations, representation of space, time, and concepts. I believe that embracing this diversity of neural algorithms and also neural dynamics is absolutely necessary to develop artificial intelligent systems that can generate movement in all those dirty, dull, and dangerous jobs and support people. I believe this will make life of these people easier and will allow even single moms and people without a handicap to have enough time and energy to pursue their dreams and to have fulfilling lives. I think these will make our society healthier and overall more prosperous. Thank you.